Hello, everybody. How are you tonight? We have Jess, who you can hear her keyboard. Hi, Jess.
Hi, sorry guys.
No, you're good. I just caught her with a quick, we're going to start now. So, all right. This is C as an additional language. Topic 4, functions. For those of you who are here last week, this is a completely different show than last week. Actually, not at all. That was just topic 3. We were doing while loops. We were doing iteration. We were practicing. We were covering the real types we're supposed to use because I never write int and char, and I use those old-fashioned types. Is that right, Jess?
Never, ever.
Totally.
Ever.
Never.
Totally, never.
Ever. No one look at the VOD. And hello, everybody in chat. We have Okigon. We have the Enceladiosaurus. We have Fafi.
It's me.
We have Lopone. All right. Yeah, it's a party. Now, by the way, I would like all of you to know who were watching earlier, those dice, that's a real camera. I rolled that 20, that double 20 right in front of you. I'm just going to take a moment and think about that because that just blew my mind. I want to just, let's look at it.
I'm lucky.
I feel like we never just look at that double 20.
Can I have that luck in real life?
Position it. I mean, like you saw the roll. I threw it. All right. I feel good about tonight. Jesse is very lucky. I'm sorry. The Enceladiosaurus is very lucky. Clearly that's not coming from me. Okay. So, great. Well, we're going to be following the same sort of format as last time. I think that works better. I think the Enceladiosaurus was happy with it. I think I'm saying her name right.
You are.
Awesome. So, yeah, Loafbone, we're going to go buy lottery tickets. That is just, I completely agree. I'm going to try to be succinct because rather surprisingly, one of my favorite streamers, in addition to the Enceladiosaurus, happens to be doing a live music thing tonight. That's 88-bit music. So if I'm rushing too much, Enceladiosaurus, just stop me. Be like, no. Stop rushing to try to go listen to video game music live on piano.
Oh, wait. So you have to share the link, obviously.
I am sharing.
Watch the music.
I'm not sharing. We're rating.
Yeah. All right. There we go.
We're going to do that later. So, anyway, no. So I don't want to rush too much because, general format, we're gonna stick with kind of doing the more learning stuff up front and the more just general stuff in the back, and probably not as long as the last time. So anyway, our main topic for today is functions. So we just got a new version with all of its brand new bugs of the this is our overall topic lesson plan. This is our new version of the editor, and it now supports group selection. So these code changes were just checked in. So theoretically, what did I just highlight in Enceladiosaurus?
You've highlighted main parentheses, the stuff inside of the parentheses.
Yeah. You hear that, everybody?
Woohoo!
Actually, she could be looking at the stream. I guess that's not a good.
I saw it before the stream.
Okay.
I knew it before it was cool.
Okay. All right. Awesome. So she gets kind of a low lag version of selection. So the tool's getting a little bit better. Great. So here's where we are. We're done with all that stuff. There's not many topics left. In C, C is a pretty simple language. That's part of why it's so portable. That's part of why it's been around and stood the test of time. There's not much in the language. So we just have functions. Then we're going to be using functions with standard IO. Then we're going to do a little more with dynamic memory. Today we're going to be using static memory. And then we might touch a little bit on missing parts. And that's pretty much it. At that point, you're a C programmer.
No. Nope.
Yeah, it's just practice after that, really. But,
oh, good Lord.
So we're gonna be here. Let's get to this stuff. So I've got the glove on. We're ready to draw on the board, and I can look cool with my partial fingers.
I am so ready for this.
All right, let's find the whiteboard. Okay, so here we already have this up. I'm going to knock these beautiful 220s aside, and we're going to get to drawing. Okay, but we're not going to use that green because I've already used green. Okay.
But green's my favorite color.
Okay, then I'm going to use a different green. Then different green. Okay, you like green, huh? All right, cool.
It's the color of plants.
It is, and apparently we have more optic sensitivity to green than any other color.
The sun's spectrum, its light spectrum, its EM spectrum peaks in green.
Interesting.
Mhm. Just a little factoid there for
Yeah,
chat.
little factoids. I'll just
I'm
throw
full
those
of them.
over here.
Factoids.
Sun more green. Okay. So, all right, functions. What are we going to do with functions? Functions are about isolated call spaces. So we have, actually our first function is already up on the screen, and the Enceladiosaurus is going to memorize it in her bones.
Copy and paste.
We're gonna go beyond muscle memory on this one, and that was a bad G, so I'm gonna undo that G. We're going beyond muscle memory here, and this needs to be bone memory. Okay, so
Oh, Lord.
and like we're used to seeing, this is sort of this is the name of whatever our function is. This is the return type. So this function has to return an integer. And these two are kind of some magic from the operating system that I have not described. But tonight we're going to find out what they are.
Ooh.
I don't know if we're entirely ready for that, but we're not going to be dealing with this system function. This is kind of like this is always your starting point. So the C runtime, the startup script specifically, it's called CRT0. You don't need to know that. Will always look for this symbol, and it will start there. And so that's kind of like where the action begins for your program. So we are going to make our own functions. Now, this thing is not going to go find it for us, so we're going to have to call our own functions. And Enceladiosaurus is already familiar with the general style of functions, but we're going to be talking a bit more about like what's happening at a lower level, because Python kind of does all this magic for you, and probably doesn't give you a very good description of what the machine's really doing. But we're gonna be doing a little bit more. Now we're doing C, so we're getting closer to the machine. So I'll give you a nice little computer, classic PC here, with a light and a little turbo button from back.
Is that what that is?
Yeah, that's okay. All right, let's get rid of that. Art is not my strong suit. Okay, so what happens with a function? Function's all about kind of like an isolated place. So we have in here, we just had our main function, and in it we were declaring stuff like integers, characters. What were some new types that we learned, Jesse?
Uint and various bit types _t.
Yeah. Like uint 8.
We also had long briefly.
Yeah.
Double, I think, at some point, but I don't even. That one's still hazy for me.
No, that's fine. Long is usually the same size as int these days, but could be longer. And how do we find out how big they were? This is just a quick recap from last time.
Size of.
You got it. Okay. So,
which is an operator.
Yes.
Not a
yes, it is.
I remember.
So that is an operator. It's not a function. So it is in the base language. And hello, Sunny. How are you? Sunny is commenting that there's also a long type and all sorts of other stuff. But at this point, by the time we kind of got here, we're going to start using these new portable types as opposed to these kind of like older school types. All right. So what do these types do? They spell out how much memory, right?
Mm-hmm.
So when I was doing like, if this is like, let's imagine we had a world where there was a 16-bit long, a 16-bit int. This was like kind of back in the day. And that nowadays is referred to as a short, but
it's small.
Yeah, so like if this was 8 bits wide and from here to here, and this is 8 bits wide from here to here, so we got 16 from here to here. This is kind of that short type that still exists, but nowadays int is really almost always 32 bits, so we have to go in here and here. And there's no standard 24-bit type. So this doesn't happen as a standalone, but this does happen as sort of like int and long, until long sometimes becomes 64 bits and sometimes it's 32, and that's why we stopped doing that. So we start using these portable types. Okay,
Right.
this is important because we're spelling out exactly how much memory we're using for every one of these variables. And that's a little different from Python, because Python, I could start off saying x is 5, and then a few lines later, I could be like, well, x is now, NC. and that's kind of fine in Python, right? It's not exactly preferred Python, but you could do that. Dynamic languages tend to allow things like this, like JavaScript will definitely allow it unless you're using like a TypeScript variant. But so this is kind of like fine. You can sort of do this type switching depending on context. But C types are very literal. They mean like how much memory. And when we start talking about functions, all of these types, whenever we declare a variable, it's owned by a function or it's owned in the global space. So that's really our only two options. We can either, like, if we say like int x, then either this thing is outside of main. I have my declaration for main down here and I'm sort of doing whatever.
I thought nothing goes outside of.
We didn't. Yeah, that's style. So if outside of any function is the global space, and we try not to put things in the global space anymore. We learned a long time ago that that's kind of a naughty practice. Back when machines were a lot more limited on memory than global space, we tended to use global space a lot more than we would use sort of function space. Nowadays, we tend to prefer not to do this because it leads to a lot of bugs, because you might forget like which functions edit X. I don't know. Maybe main is going to take a reference to X. Maybe, func A is going to take a reference to X. Maybe func B is going to mutate X. Maybe func C is going to define its own version, its own variable called X, which is not the same as this one. So this kind of becomes like chaos very quickly, right?
I can see how that would be messy and that it would be difficult to kind of. I'm used to the mess. Like literally, I started with Python. So when you were describing, oh man, this is messy, that's the mess I live in, my friend. But it makes sense that there could be a better way.
I just have to comment that I think it's amazing. Nightshade Dude recognized what can you opened.
That wasn't PBR. That wasn't. So I will have you all know, thank you very much, that was not PBR.
Okay.
I'm classier than that. It is White Claw.
Not
so there you go.
PBR. Okay, so that's good.
Gotta hydrate. Yes.
So okay, so it depends kind of how do we refer to these different areas where the variable could exist? They're called scopes. Okay, so I don't know how much scoping you kind of did in Python.
So I think this, let's just say none, because to me, scoping sounds more like words that I've heard used in a consulting context, really, than I've heard applied to program. When you say like the scope of a function, to me, there is an intuitive understanding of what that means, but I'm not sure if my intuitive understanding is really the technical definition that you're looking for.
That's fine. Your instinct is probably right. So if I have like a main, imagine this as sort of like boxes. Okay. So if I have a main scope and in here I define int x, and then I have like another function, which I'm going to call func A, and in there I define int x. This is valid. Okay. Because this x stays inside the func A box.
But they are different x's.
This x stays inside the main box. These two x's are not in the same place in memory.
And they also are not the same.
That's correct, because they're different memory locations. This is C, so a variable is literally a location of memory.
Okay.
So, the whole type thing is really just about telling us how much memory is related to one variable, but ultimately it's just specifying like, I want you to, like, this is really going to be living at some address in memory. So memory we can view as just this massive stack of stuff. and it's all these locations, and each one is 8 bits. And, you know, if I'm doing an int, then I'm taking 4 of these. So this might be X. And if I take a char, I'm taking 1 of these. So if I do like, you know, if this is int X and this is like char Y, then that's going to be this box. And then if I don't care about byte alignment, which at the moment I don't, then, which we'll get to that later, then this might be like int Y. Okay, now because of this scope thing, I can reuse the same variable name because this int X applies to like func A, whereas this int X applies to main. So despite the fact that they're both called X in sort of the program text, they're not the same variable because they actually point to different locations. They're different parts of memory. Does that kind of make
makes
sense?
Perfect sense.
Okay.
Absolutely.
So that's really what scope is about. Scope is about like kind of drawing a line saying, okay, this stuff below here, this is the main scope. And this stuff up here is the func A scope. And this next chunk that we're going to do, that's the func B scope, and so on, right?
So it kind of reminds me a little bit of in object-oriented programming when you're using classes, how you can have kind of, you know, instance variables and you can have class variables. And so I'm probably not using the right technical terminology,
classes come
but
much later. but they do have this scope notion kind of associated.
Well,
with
what
it.
I mean there is that like one, just because like if you have something that is encapsulated in a particular function or instantiation of a class, like that applies to that relative instance only. It is not a universal. And if you have something that is outside of that, then it could perhaps be a universal, but you have to be very careful about like what things are relatives and what things are universals. And I understand that's like I'm using terms here from philosophy and math and also my understanding of programming, and I'm not formally like
Actually, I think it's
programming educated. So
I think it's probably your field that's biasing you there because universal is probably
global, okay.
Something that you think more about. But programmers are much more down to earth, and they're just global's already pretty big for a programmer. So, but you should just drop that term universal. Basically, your instinct is right. I'm agreeing with Fafi. And Fafi, I'm sorry, I shouldn't have answered. So I should have.
No, we're all excited and we're all enthusiastic. And
it's totally fired up. So my bad. Okay, so how does the compiler determine how much of this? So if this is all of RAM, then how does the compiler determine how much of this is related to like main versus func A versus func B?
I feel like this is oh shoot, I should have written down the term that you said earlier that you were like, we're not getting to this yet. It's like bit order or something. Is that
there is
like in terms of
a bit order thing. They're telling me to turn you down a little bit. I think I've got the volume not very well balanced. Can you say something
for once? Hi. Usually
Hi.
I'm very quiet, so I was trying to maybe like project a little bit more because usually I get told that I'm too quiet. So for once I'm not.
All right. Yeah, in chat, let us know how that sounds. Sounds ballparkish now, is what Moshi's saying. All right, maybe I'll go down a little bit more. Anyway, keep giving us feedback, chat, in case it's not right. Okay, so you are right about this endian thing. That really applies to like left to right or right to left within a given type. So if I'm like talking about an int and I'm on a big endian platform, we did talk about endianness a little bit in the first session, which was a mistake on my part. then the most big endian kind of works the way our normal numbers work. So if I have the number 1000, which digit is the most important?
The 1.
Yeah, it's the most significant digit is on the left.
Right.
So the most significant digit is left. Okay, so that's kind of big endian. Little endian is the reverse. So the most significant digit, I would write this as 0001 if I was going to write it as a little endian number.
Okay.
But the number value is the same. Like either way, it doesn't matter if you're somebody who reads left to right or if you're somebody who reads right to left. They're both 1,000 once you agree on which way you're going to read for this given architecture. So,
yeah, it's convention.
Yeah, it's really convention. We generally, computers use the little endian architectures kind of won out over the big endian architectures. But network byte order, which is kind of how the internet works, uses big endian. So that's going to get messy later. So, and yes, I really like Nathaniel Bumpo's example that this would be big endian date writing would be like 2020. Let's use today's date. What's today's date?
That's the one he was giving you.
5/4 versus little endian would be 4/5/2020, and American would be
broken endian
would be inside out endian, which would be 5/4/2020. Because reasons. Okay, and too bad, Nathaniel. Okay, so broken endian, nice. So, yeah, we can. I'm going to borrow from Silicon Valley and call this inside out. Like inside out compression. Okay, I don't know if anybody watches Silicon Valley here, but
there are too many dudes in it.
Yeah, it's a documentary about Silicon Valley. It's not a comedy. So, and for exactly what you just said is true. I used to refer to it as Man Jose because it's San Jose is really Man Jose. Okay.
I just what there's a certain thing for me where I promise I won't go on a tangent, but like if I have to deal with it every day in my job, I don't want to come home and watch a show about it. Like my shows are for escapism, And
no,
sometimes
I have
escapism is like post-apocalyptic, the world is ending, but also sometimes escapism is like I don't have to listen to a bunch of dudes who think they're way cooler than they are. Sorry, but like, well, I get paid to do that. I don't get paid to watch that show. So
we'll let's throw that on the topics list. So,
yeah, we'll put that on the
Silicon Valley dudes. Okay.
Oh boy.
All right. So we're gonna come back to that one. So all right, back to my question. So RAM is all about breaking up RAM. Programming is all about breaking up RAM kind of into chunks. So how do I know what's going to like where the line is for this stuff is main and this stuff is func A and this stuff is func B?
I'm guessing the answer is scope.
And all of this stuff is really func C. And scope is actually kind of like where these lines are, right? So scope is like this is func C space and this is func B space and so on. But how does it know where to break memory? Because memory is like it's got to memory's not divvied up on the chip. Right? It's just
is it just how much memory you use in that particular operation?
Yeah, because how do we declare how much we use?
Well, we tell it.
We declare our variables. So that's exactly we specify. Okay, I want like an int, to be here, and the compiler doesn't really care what you call it as long as it's something valid. And then we want another int to be here, and how many bits is an int normally?
16.
It was in the example that I showed before. That's really not.
I mean, modern 32.
Modern 32. Okay, so It says, okay, fine. 32 bits is going to this int, and 32 bits is going to that int. So if each one of these blocks is 8, how many blocks do I need?
Oh Lord! If each of those is 4, 5, 6, 7, 8, 8 and. Is that 8 and 5? 13 times 8? I'm trying to count here. Are you just talking main or are you talking the whole RAM?
Oh, yeah, sorry. Badly
for main 32. For main 32.
If I've got 2 ints, then each of these 32s, by the way, we're mixing bits and bytes. So here we're talking about bits, and we could be talking about modern bytes, which are really octets. And octets are really all about 8. right? 8 bits in 1 octet. So I can think of a int as 4 octets, right?
Int is 4 octets. Yes.
Right, which is the same as 32 bits.
32.
So if I've got it now, if I've taken my memory and I've broken it into octets, which is typically how memory is organized these days, then I need 4 of these for 1 integer. Right?
Right.
Okay.
Yes.
So if I define 2 integers, how many do I need?
64?
Double. It's 64
Well,
bits. So how many bytes?
8.
Exactly. So
Okay.
yeah. So
Math.
not making a mess. Let's make a bigger one. So all right. So if one of these is 8, then this is an int worth of memory, and this is another int worth of memory. All right. So if I was calling a function which had func a, and it has 2 ints, I have int x and int y, the compiler is going to read this and go, all right, one of these is 32 bits, which is 4 bytes. So you need 1, 2, 3, 4. And the second one is going to be the same thing, 1, 2, 3, 4. I'm going to say that that's the end of my function. So func a, you get this much memory. So this whole thing about declaring variables is about determining how much RAM we're going to give to a given function. Make sense?
Yes, I would say that I can see serious downsides to this, just in terms of, I guess when I think about trying to be this conscientious about my memory usage, I don't have to do that in Python. Okay, but I'm thinking let's just say that I could,
Python.
and but thinking about how much memory I'm using in a lot of cases when I am, for example, using machine learning and things like that, a lot of times there is kind of an ambiguity or an unknown element in terms of either the parameter space that you're exploring or what kind of you might expect as a fit to that parameter space. And I can't imagine knowing. It's like knowing the answer to a test before I take it.
We have to know the answer. So in the case of C, which is literally like compiling something to run directly on the machine, we have to know exactly how much memory to allocate to each function.
Ew.
That's kind of how the language was designed.
I know. And I understand, functionally speaking, I understand why that's a necessity. And it does make sense. But when you get into more of the exploratory element of a lot of modeling and whatnot, I find that could be overly restrictive. Or that it would take
very
a lot
restrictive. And yes, it takes a lot longer because you actually have to spell out everything you're going to use, and maybe you don't know. But we're going to get to that shortly. Okay, so the important thing is to kind of build this concept in your head that each of these functions kind of has like a fixed part of memory that's going to be associated with it. This, by the way, is called the stack. So stack is probably not a term you might have heard in Python land.
I haven't heard it. I think in this particular, I think we've all heard kind of like full stack development and stack used to describe that kind of like application.
Yeah.
But I think this is not an application level stack.
That's a different kind of stack. That's like, you know, like for example, Linux, to use like an old one, like Linux, Apache, MySQL. Actually, MySQL is usually kind of running at the same side.
Oh, sad face.
And
not to
I don't know. We'll do
knock SQL, but
do Python, or do you want like PHP up here? And so somebody who's full stack was somebody who did all of this, right? And then also the client, right? So this is usually like HTML and JavaScript and
CSS, that stuff. Yeah.
CSS or whatever. And so somebody who is full stack,
the people who can make it look pretty.
Yeah.
And I'm not one of those people. So,
yes. In that sense, like, yes, we are stacking stuff up. But no, in this case, the computer version of a stack is actually a lot more like a stack of coins than it is like this, because Apache and MySQL are kind of running at the same level there, so they don't properly stack on top of each other, right?
Yeah.
So, but if I have a stack of coins, like, I have this coin and then this coin and then this coin, like, I can't pull this coin out very easily, right?
You're right.
I mean, I'm going to have to sort of like take this one off and then get this one and then put this one back on. And, if, and that's kind of important, because that, if I have like a lot of these, like, the difficulty of this problem kind of scales with how many are there, right?
Right.
I mean,
that makes sense. Like, yeah, it's like one of those logic puzzles of, restack these boxes or something. And yeah, okay. Yes. Sorry, that was me hearkening back to like little video games I played as a kid. But yes, that makes sense.
Yes. And in this sense, we're bound by gravity in the real world, mostly. So we tend to think of stacks as growing up because, gravity's sort of pulling this stuff down, right? Okay, well, in computers, we do it exactly the opposite. The stack grows down.
Oh boy. Okay. Well, so our stack is in space.
Yes.
Okay.
So this is one of those, like, the stack typically grows from high memory addresses down to low memory addresses.
So you fill in the big things first, and it's kind of like that idea of like you have 50 rocks, like 20 of which are big and then 30 of which are small. You want to fill a particular jar. You don't put the small ones in first. You put the big ones in first, and then you stick the small ones where they fit.
Well, except that the catch is kind of like what they're bringing up on that I was sort of like touching on briefly in the last example, what they're bringing up in chat. Like with the gravity stack, I can't pull out something here
without everything crashing,
without everything falling down, right? And so it's sort of the same way with like the computer. Like if I try to like pull out this piece of memory here, like it's not gonna work. Like it's kind of not the mental model. Now Meatball is bringing up Meatball Ceros is bringing up kind of a good point, which is that the stack growth direction is actually architecture dependent. I can tell you that the stacks we're going to be dealing with today, they're all going to be growing down. So kind of this is pretty typical on Intel architectures.
When we're talking about stack here, like, can we root this in some physical reality? Like what no, not coins, but like literally when we're talking about the computer, like I understood the concept of like allocating memory space, but when we're talking about these stacks growing in different ways, like what are we talking about when it comes down to the hardware?
We're talking about RAM.
Okay.
So,
all right.
So how much RAM I have is kind of this is one of the limiting factors of programming, right? So if I have, nowadays, how much like memory does your computer have?
RAM wise, 32 gigs.
Okay. So this is massive. Okay. this
is my divorce present to myself. So yes, it is massive, beautiful, and it's a beast.
Yes,
it can
it's
do whatever I want
it's wonderful.
To.
It's like so much memory. But like back in the day,
it's my baby.
Like C was being created. Like these things were more like, so that's 32 gigabytes, and giga means like billion.
Yes.
Now,
it does.
It's
10 to the
it's unfortunately it's not tens because it's really we're using powers of 2, so
so 2 to the
2 to the something, but it's going to end up being around like 32, like 33x billion, kind of. We'll calculate it in a minute, but so this is a really, that's a lot of, and that's in bytes. Right.
Yeah,
so
we've been counting these things so far in our examples. So obviously it is a significantly much larger amount than we have been discussing previously.
And Miss Tran is having fun talking about this is a quote from Bill Gates, which was back in the day, 640K is more memory than anyone will ever need, and that was back when 320K was kind of normal. But back when C was being created, like 16K was a lot. So this. Jeez. Like you used to be able to like kind of count how much memory you had like directly. So you could, like the Nintendo that I'm going to be programming later on in one of my shows, like that's got 2K, but you actually lose a bunch of it, so it's really like 1.5K. That's an NES. Like
and so you're doing NES.
Yeah. So just to give you a sense of like, by the way, that'll be partially in C, and I think
make sure you let me know when you do that, because
that
sounds exactly like my kind of hacky.
Well, the funny thing is, if you look at the course program, it's actually later on. So, okay, so we are going to be doing some of that a little bit later, but if you're interested. Otherwise, I might just do it on the regular show. But this kind of size is really different from dealing with like that kind of size, like 32 gigs. So we're going to be, when you're thinking about memory, let's think in this space, which is kind of like where the language designed, and then they sort of added on stuff to be able to deal with like larger sizes. And so, yes, and as Strophium pointed out, a teraflop was a myth in those days. So, did he talk about flops with you?
We didn't talk about it in C#.
Okay, so that's floating point operations per second. So it's basically like how much
flops are 10 to the 12 floating point operations per second.
Yep. So that's a lot of math. That's the kind of math you need to be doing neural networks. Okay, so great. Let's get back to functions. So each of these functions has its own space. So I've got my main space, and I've got my func A space. And when I defined how I specify these things, I gave them lines that looked like int main, and then some stuff here like int argc and char argv.
Yes.
Okay.
Your arguments. Mm-hmm.
Right. I'm spelling out to the compiler like this is exactly how much space you're going to take.
Yes.
Especially when I take this stuff plus like whatever's going to be in here, like if I do int x and int y and all this other stuff. That's spelling out on the memory like, okay, this much is going to be for main. This is called a frame.
Frame. Okay, that is the first. I mean, in a cinematography way, that is the first time I've heard that. Okay.
It's like precisely called a stack frame, but we're going to be kind of building stack frames today, and this is kind of important in terms of ownership, and that's the reason I'm being pedantic about it. Because that if I have like an int x that's in the func A stack frame, that does not mean that main gets to access it, and that's really important.
So these are like contiguous but non-interactive chunks of memory.
Yes, we can get them to interact. It's naughty. Generally, we don't do that. We're going to use some different techniques. We're going to get to something. This is we're working on the stack, which is kind of like the normal space for that. That's where you've been declaring stuff when you do like int x, int y, all that stuff. Later on, we're going to be talking about something called the heap. And the heap typically grows the opposite of whichever way the stack grows. So if the stack... But
when we talk about direction of a stack, I still I get the stack RAM, like direction. What does that mean when we're talking
We're going to get to that.
Reality.
There's a reason that I'm not directly answering your question. The important thing is that
I trust you. Go for it.
They grow into each other on typical architectures. So if the stack, if you're on an architecture where the stack is growing up, which is not very common these days, then the heap would be growing down. And if you're on an architecture like what we're going to be using shortly, where the stack is growing which way?
Down.
You got it. If the stack was growing down, like say on your typical Intel architecture, then the heap would be growing
up.
You got it. So
okay.
What do you think happens when these two meet?
I'm sorry, I literally have no idea.
You get to keep both pieces.
Okay.
So that's a crash out of memory, basically.
Oh, okay, all right.
That's you don't ever really want this line to hit. Okay, so that's kind of an obscure that'll happen. That's not very likely to happen on your 32 gig of RAM monster. that you have. But, back on like an NES, like that's downright likely that you're going to smash into each other. So you have to be very careful about smashing the stack. We're going to get into that a little bit later. It's not going to be a big problem for us today, but just be aware that it's important. And Strophium, don't go stealing where I'm going with that, but we're going to get to that in a little bit. Okay, so great. We know how many variables we have, right?
Yes.
And if I add all them up, so let's sum them all up. Is that the right sigma? I haven't drawn a sigma in years.
That is sum. Yep, you're good. You're good.
Okay. All right. So
I got you.
If we sum up the size of all the variables, then that's going to be plus a few things, which I'm not going to talk about right now. Then that's going to be kind of like the size of the stack frame.
Right. Okay. And I mean, wouldn't certain operations take? Is that included in the plus few things?
There's very little in this plus few things. It's actually really just maintenance stuff.
Okay.
So what are you worried about not fitting in there? So with C, keep in mind, this is not Python. With C, you declare exactly what you're doing with memory.
Right. And
no ifs, ands, or buts about it. And if you don't declare it, C will just interpret
it. So let's say I define a function in C in Happy Little Land.
Yes.
Like the output is going to be, I don't know. The output is going to be
Pick
a very,
type.
I don't want to type.
Well, here, let's do a function that adds two numbers.
A small integer. No, but here, so this is my point, right? It's like if I pick if I define a function that takes in, say, two integers,
okay,
right?
So int, what do you want to call it?
Exponential.
Exp. How about exp?
Right? And it takes the first int and it raises it to the power of the second int and it returns the result.
Can we name them? Do you mind if we name them?
Yeah, bottom and top.
Okay, bot, and I'm just going to abbreviate. Bot, top. Okay.
Right.
And what does it return?
So it returns it returns bot raised to top.
Which is what type?
I'm trying to think of an example where the result, the operation done. No, wait. It doesn't return that. This was the example that I thought of was the operations done in the body of the function. For example, I raise something and then take the log of it or whatever. So like I use more memory in the body of the function to do something and then I shrink it. So just by defining, output is small, inputs are decently small, but what happens in the body of the function takes a lot more memory. How do you handle that? Was basically my question, and I was trying to consider like an example, but probably botched.
So can I call it exp and log?
There you go. Yeah.
Okay. So we have, and I'm going to keep your bottom and top.
Okay.
Okay. And what type is it going to return?
So we're expecting an int as well.
Okay. You're going to return an int. Okay. So that's your function specification. Okay.
Yes. And I would imagine that is kind of what tells C how much memory to allocate for that particular function.
No. That's just how much memory to allocate for calling it.
Ooh, okay.
Because in the function, you said you're going to need a little working space, right?
Right.
So let's call that A. Excuse me. Okay, so I have an int A, which is in that function, right?
Mm-hmm.
Okay, so if that's all my variables, how much memory am I using?
Assuming that they are...
And we're for now on, I'm only going to talk about 32-bit ints. I've already told you that there's other ones. That's why we use the new types. But from now on, for us, let's just always say int is 32 bits.
We're using 96 bits.
Well, let's use bytes.
12 bytes.
Okay, because bottom is 4, top is 4, the return type is 4. That's 12. Sorry.
12. Oh, and A.
And then
so
A.
I assumed return A, so that was my fault. So yes. So
Okay,
we
so
have
this
16.
stack frame needs 16 bytes.
Right. I see. So that was my mistake when I was
Plus
thinking
stuff.
about the allocation of memory.
I'm-
The distinction between how much memory it needs to call it versus how much memory it needs to execute the function. That I'm good.
Yep.
My brain has been corrected.
Now, if I have another, if I've got main down here, I'm not going to fully specify main, but if I've got main and I have int a, what am I? This is not the same a, right?
No, yeah, it's different because it has a different space.
Because they're in different frames.
Scope. Yes.
Okay, so I've got my, in the example, exp and log, and main. Main has its own a, and exp and log has bottom, top, a return type, and a, right?
Mm-hmm. Yes, those are 4 components.
And then plus the little bit, plus stuff. And I keep not telling you what stuff is.
It's okay.
Okay. But pretty much that's how it ends up getting laid out in memory. Now, we're not going to talk about optimizing compilers. We're not going to talk about byte alignments. I'm going to stay with a relatively simple model of a computer, as good as I can. Now, Nathaniel is referring to something that happens because of optimizing compilers and what's called the fast call convention and a few other things that get invented.
God. Okay.
So
Sorry, there were like 10 things in there I didn't understand.
Don't you worry, because we're not going to worry about that. What I'm going to say to Nathaniel is we're going to start with the classic stack register model of a computer. So this is it. The modern computer does a bunch of things to try to make this faster. But I can tell you that conceptually, that's not that important. Like, it's more important that you understand, like, when you're in a frame, you're in a frame. Okay. Actually, to Nathaniel's point, it's probably a modern compiler is not even going to create your function at all. It's going to unroll it. So it's actually going to use nothing on the stack. But we'll get to that later. Okay. So does this all make sense?
Tentatively, yes.
Tentatively, yes. We're going to be coding.
Okay.
So,
I mean, there is this like small, like 12-year-old. Well, I was much older actually. I don't remember when Minecraft became a thing, but there is this small desire to answer equipolant. Excellent name, by the way. Where I have wanted to understand things for so long, kind of from that hardware level all the way up, but I don't think that is in the scope of what we're talking about now. So I would say hold, please.
Oh yeah, we're going to be later on in a future lab session. We'll actually look at memory directly. So I can tell you that this is going to help you conceptually with that. But the important thing is to realize that, like, you have to kind of declare. This is C. It's not Python. You can't be willy-nilly about your variables. You got to declare everything you're going to use, and you got to be very explicit about, like, what you're what you're doing. Now
I just have to know what I'm doing. That's the problem. That's
Well,
deep, like, at a fundamental level. My issue with C is that it assumes I know what I'm doing, whereas Python doesn't make me know what I'm doing before I do it, which is really nice.
That's kind of the magic of Python. Okay.
Right. I mean, I have to know what I'm doing before I do it. Which...
So now that we know what a stack frame is, roughly, that's the basis of us building what's called a function. Okay. Now, back in the era that C was created, there was a debate between what's a function and what's a procedure. And a procedure was just a set of steps to do something. A function was mathematical. It was like f of x. So what does f of x do? It returns a value. Mm-hmm. Right?
Now we're in my happy place.
It has to return a value, right? So
yep.
I'm not allowed to, and yeah, beer open. So
okay, no, I'm good.
I'm not allowed to not return a value. Okay, I have to return a value if I'm having a function. Okay, and a procedure was all about just do this stuff. And maybe there's side effects, maybe there isn't, but it does not return anything. So we didn't use the term function. Now, C got rid of that notion, right? So it said, okay, there's no such thing as a procedure anymore. So everything is a function. It's just that sometimes functions don't return anything at all. And if we return nothing at all, that's the void type.
Strophium, so much of yesterday makes Sorry.
I don't know what you talked about yesterday, but void is all about...
So we were working in C#.
Okay.
And there was a command that I was working with, which was void something. And I was like, wow, this is a really morbid way to say death.
Void.
Because we were working with functions.
This is...
Right? And I didn't realize that
down
that's
at the bottom of the hole.
That makes sense now. Yeah, all right. Well...
Okay, so...
Sorry. So there was a connection made for me, and now things make more sense.
This is kind of where this gets introduced to the language. Now, void actually takes on a different meaning later on with specification, but we'll get to that later. Like, where it starts is this distinction between a function and a procedure, and C sidestepped the problem by saying everything's a function, it might return void.
Okay.
So if we don't know what to return in our function, like, for example, if we're just going to print something out, like, say, putChar, then we could just say, and putChar, what was putChar going to take for a parameter?
So it can take a character?
Yeah.
Or it can take an int?
No, it just takes a character.
Well, it interprets the int as a character.
If you give it an int, it's going to coerce it to be a character. That gets in that.
Which is casting?
Yeah, that's casting.
Yeah, see?
Coercion and casting are slightly different, but I'm not going to it's pedantic. So
we talked about two kinds of casting, and so I understand that coercion.
If you call it casting or coercion, I'm fine either way. We'll get into the differences later. That might cause Strophium to choke, but sorry. Okay, so
oh no, Strophium, don't die.
Okay, so in the case
we have to finish Pong. Yes.
In the case of like putChar, this is really all about side effects, right? Because what does putChar do? It outputs something, but it doesn't actually return anything, right? It just does some stuff, right? So we do stuff in here. We don't really compute anything. We're not doing like an exponential and a log where we want the value back, right?
Right, because in that particular case, what it's doing is that it's printing. It's not returning, it's printing. It's printing to like an output, right?
Yeah, which it doesn't return. It just...
Exactly.
Okay.
So we can't say like x equals putChar because that doesn't make... That
yeah, no, I don't. I'd have to check the actual type of putChar. putChar is a well-defined function, so it might return like how many characters it actually output. Like I'd have to check, but that would be silly in the case of putChar. I'm pretty sure it returns void. I'd have to let me look. Just I don't want to tell you the wrong thing.
Yeah, you're fine.
Okay, putChar actually does return an int, so this is
well,
which is that and putChar returns an int because it says like whether or not there was an error. So it's using this. Uh-oh. Come on, drawpad.
Oh no! Have we lost? No, we can't lose it now.
Drawpad.
No, we need
okay,
it.
Good. We're back. Okay, we're good. So putChar actually returns an int, and it's using this as sort of like an error message. But that's not really the same as like doing a like putChar, like I mean, the real reason you're calling putChar is not to find out whether or not it got an error, right?
Right, exactly.
You're sort of hoping for the side effect in this case that the thing shows up on output. Okay, great. Well, let's go write a few functions. How's that sound?
Oh no. Okay. Yes. Yes. Yay.
Okay.
Sorry.
There's one thing that I do want to specify before we move on. The order that these parameters go. So let's do a simple function. So give me a function that I'm just going to call it add to numbers. Add to.
I'm guessing it returns an int. So
yeah, that's a great guess. Let's make it return an int. And what does it need to take in? I mean, oh, you're typing. Sorry, I was looking at the whiteboard. So
I tried.
No, that's totally fine. Okay. First of all, this is not in main.
Everything is in main.
No.
No. But I thought the whole thing was.
Main is its own function.
But. Everything we've done so far has been in main. This is new.
Yeah, we're moving out.
I thought everything I had to do was in main.
No,
so
no, that was.
I thought main was just like run the program.
That was the old world. That was topics 1 through 3. Okay, so
here be dragon. All right,
yes,
we're good. Okay, so main is kind of like and
main is just the first
fancy
function.
Pants and people in chat they're happy for a second.
Strophium
but
singing.
main is like that, you know. If
a whole new world.
God. It's like if in Python,
a new fantastic point of view. All right, I'll do that in the Scotch later. Sorry.
Sorry, I'm trying to.
Yeah, a little excited. Okay. Snap back to reality. Oh, there goes gravity. Okay.
Okay. Yep. Professionalism. All right. So if I recall, the sort of metaphor that I use to remember what main was is it's like when I specify a certain behavior for a script when it is called as main in Python.
Uh-huh.
Is that what main is?
Except in C, it always starts at main.
Well,
that's kind of where Python picked up that main word from.
I feel like this is Python's the millennial in boomer town right now.
All right,
like
so
you didn't have to walk uphill 2 ways to go to school.
Yeah.
You know what? Like dynamic typing's kind of awesome.
Yes, yes, it is. Okay,
so here if I were to call add 2 numbers, it would be in main, but I define add 2 numbers outside of main. Is that correct?
Not 100% sure I followed that, but try that.
So let's say I write a script where I want to define a particular function to add 2 numbers.
Yep, you did that correctly.
In main,
I'll tell you right now.
So when I run this particular script, I would like it to print the result, whatever. When I run this thing, whatever C's fancy
program.
Word for this
it's
thing
called program.
Right. I want it to print the result of add 2 numbers, and I specify 2 numbers. So I would define add 2 numbers outside of main, but I would call it inside of main and print the result.
Yep.
Yes?
Yep.
Okay, then I follow you. I'm good. All right.
So do what you just said.
Oh, crap. All right.
You've got your function defined.
I don't know if I can do this as Python.
Wait, hold on. One step at a time.
Yes?
Let's define a variable and store the result. All right, so just define x. Now x is different from the other x, right?
Yeah, because our scope is different.
Right. They're in different stack frames.
3 and 4. Oh, nope. I know how to do this. Oh, poop. Hold, please.
Holding.
This, I think this, and then this, and then that.
All right.
Oh, Lord.
Do we want a new line too, just for fun?
Oh, yeah.
Yeah, except the other way.
Oh, yeah, because it needs to be at the beginning.
Yeah, you've been in Python C# too often. No. Let's do.
What do you mean?
Oop.
Oh, Lord.
Okay.
No, I'll stop. I'm sorry. Go.
Okay.
I will stop clicking things.
This way. / not front slash.
Oh! Windows / crap. I'm sorry. That is a button I never press. Like, I'm used to Python on Mac in a happy land where that particular symbol I never need to use. So, all right.
Okay, so try it out.
Oh, no. Okay. There's going to be some sad error. Oh, no.
No,
Hey,
you got it.
Hey. So
right.
I will tell you this. Whenever I write a program, not a script, in any language, but particularly in a new language, and also, decently complex in Python, if it runs on the first go and it's not as simple as add 3 and 4, I never trust it.
Yep.
Like, it's this disturbing feeling of, excuse me, I just wrote like 50 lines of code and they ran on the first try. The universe must be broken. And I spend more time than I would debugging trying to make sure that it actually did what I think it did. Because it's an unfamiliar feeling.
That's true, and also because
it's foreign to me.
You probably never got a heavy model of what the computer's doing.
Well, that too, but
so we're starting there. But let's go a little bit further. Oh, and Equipolent, thank you for the follow. Sorry, I missed that.
Oh, yay! Yes, everyone who's from my stream, follow some coding guy. That's a command from your leader.
from dear leader. Okay.
Oh, no.
No. Sorry.
No. I would
no
say
politics.
I'm a
politics.
I'm a fascist leader of my Discord. It's okay.
Okay.
There is no democracy.
So
yes, I'm listening.
Great. This is how we add two numbers. So let's Fibonacci.
Oh no.
Okay.
Why? Oh god.
Because we got to start using these functions, right? We got to. All right. Let's. How do we do?
Definition of a
how do we do a Fibonacci sequence? It's just one.
I know it's like 0, 1, 1, 2.
And then 2. It's just
8.
add the last two numbers, right? So it's
13,
3
right.
and 5 and 8 and da da da.
13 and 21 and 34 and oh god, 30, 21, 34, 50, 55 and okay. Anyway, yes, I had to remember how that. So
we're gonna do. Let's do a couple of these. We need a
for loop.
Yeah, let's do a for loop. Let's just do the first 5.
Okay.
Miss Tran, okay, I'm not worried about algorithmic efficiency at all. I'm worried about correctness right now.
Oh Lord. One thing at a time, people. Okay, Miss Tran.
New language, complexity, stack frames,
you know what?
Algorithmic runtime.
Big O is not entering into
Don't worry about Big O. Don't worry about Big O. I'm not worried about Big O.
This is a safe space. Big O does not enter here.
That's okay.
Thank you. Okay.
The only thing we're worried about is whether or not we're going to crash because you're on an infinite loop.
Exactly. This is sunshine and daisies and
very good.
Beautiful things.
Give me sunshine and daisies.
All right. So we're going to change this. We're going to call this.
Look at this shared selection. See that? No hands.
I know. Thank you for making that a thing. It makes it so much easier to follow you when you're talking without the stream delay.
We're slowly getting better.
So
no, you can leave X and Y. All right. So actually,
I was thinking about a better terminology.
Actually, you know what? I'm just thinking that's probably jumping too many steps at once.
No, I got it.
Wait. Before you do your got it, let's just print out what X and Y are when it hits your function.
No.
No.
But I can do the Fibonacci. I promise.
Oh, you'll do it shortly.
All right. You want me to just print?
Yeah. It'll take you 2 seconds.
Percent thing.
Let's label our stuff. Come on. X is.
Wow, we're in fancy pants.
Come on. Let's grow up with our C programming. Okay. No more baby steps.
Peter Pan. All right.
Got to put on your big girl pants now.
No, I refuse. I am wearing sweatpants that I fell asleep in last night.
Also,
so you know what? There are no big girl pants here.
Okay.
So let's try. So can I do void here?
Yeah, go ahead. Let's start there.
Hey.
Yeah.
Fancy. All right. So.
And we're gonna get a compile error.
No. Don't click it yet. I gotta fix some stuff. So hold on. We don't need this. The print is already implied in my function, so I just need to.
Yeah, we don't want that in main anymore. Yep.
3, 4, that. Now, let's see. Well, of course, it's pooping itself. Did I just spell it wrong? Yeah, of course. Stupid Italian words.
It's a sophisticated.
Expected before token. Did I forget? I did. I forgot the little.
Yep.
Pedantic C.
Isn't it nice? We have errors too. Look at us, errors, shared selection. Yay. We're like crazy now.
Look, it worked.
Okay, great.
Okay, can I do Fibonacci now?
By the way, what if we did that X and Y in one line?
Oh, I deleted the wrong one.
No. I mean, I want to get rid of line 6.
Get rid of line 6.
Okay. No more line 6.
You did this before. Can I just do 2 of them? I have no idea. Find out.
Perfect. You did toss the new line. I want that new line back. So.
Well, there you go.
Okay.
You've got your new line.
All right.
Fancy.
All right. Let's
Fancy.
execute. Let's clear. Let's make sure everything's right. Okay, good. All right, run with it.
Some people. All right, I want to figure this out. So chat, you shush. I'm looking at you, chat.
Chat, you
All
shush.
Okay,
you can talk to me,
on.
chat, but don't distract her.
Yeah. You can talk to people who know what they're doing.
No, don't delete that line. Leave the line.
I don't want that line.
I want the line. All right.
I don't. Well, so let's see. We are gonna have. I have an idea. So just let me roll with this for a second. So let me think about this for a second.
So the problem with picking an arbitrary start number is you'd have to know which Fibonacci number that was. So let's just say, rather than do that, let's
make it easy for now. We'll always start with 1.
Yes. Yeah.
And we'll say how many times we're gonna do. So
I'll fix your other thing.
oh wait, no, I can do that in
Let's get out of Python mode. Except they're not commas in C, right?
Yeah, I'm getting there. Hold on. Sorry, that's pseudocode. Just give me a second. Okay, so
no, Nathaniel. Oh, yeah. Coffee with the Crew is absolutely right. This is where the music goes.
So if it's 1.
Let's do some Coffee with the Crew music. Let's see.
Actually.
All right. Do you want slow or fast? All right. I'll give you sad. Ooh, that's probably really loud. That's really quiet, isn't it?
If I do that, start at 0. It's fine.
If the music's distracting, tell me, by the way, I'll stop it.
It's fine. Oh, I can't hear music.
Oh, okay.
Plus equals itself. Next time it's 2, 4.
Oh, you kind of like to write like the whole routine first, right? Make it hard.
What did I do?
You're writing like, I go way more iteratively. I just, let me show you like kind of how I usually code something like this. Rather than jump all the way to like, you know, the answer, which is kind of like what you're doing. You're writing like a long, like, let's get the whole routine right? So I like to just,
I mean, I've done it in chunks too, but I like to kind of take a whack at it, and then if that doesn't work, I cut it down into chunks. Because I do like to see, because for me, if I do it iteratively, like how you've specified, I often don't, it's kind of like something's holding my hand. And if I do it the way that I want to, fully, and it breaks, I learn from how it breaks. And so I learn to build the whole thing better next time.
Okay.
If that makes sense.
The problem I see is I'm not seeing the program run.
Neither am I. Are you clicking execute?
No.
You know what, Strophium? I like setting. And it might just be that I'm at a place in Python where I feel comfortable writing it for seeing what happens, learning from it. But I definitely, when I first started out in Python, I wrote like, I will do one line and test and print what that line does. And then I'll do the next line and I'll print what that line does. So I definitely agree. Like that's the cautious approach that I've used. But
I think our instance crashed.
oh no, I broke it.
Oh yeah. Cannot allocate memory. I think we probably had an infinite loop run away.
Okay, so hold on. If things are loops are I, that's my problem.
No. The runtime environment looks dead.
I think that's the problem.
I think we killed the runtime environment.
No, that doesn't make sense. I like using iter. So it's that. I made that mistake.
Yep, we killed it.
I broke it.
All right.
I like breaking things. I learned from breaking.
Yes.
I learned to not break them in the future.
Okay.
I want to look at this while you are fixing the breaking.
Yes.
Okay. So.
Okay, something ran away on that. So I have a feeling that I didn't look at your loop too closely, but I think it should work again. Oh yeah, I see what's going on. You have no terminal. This is an infinite loop.
There is a terminal condition.
Yeah? To what?
Yeah, it's when this is less than or equal to. Well, oh, I need it to be equal to.
Okay. Well, hold on. Let's go with your.
I think that might work better.
Let's try your less than.
No, because that'll fail from the start, and that's not what I want. I see the error there. I want it to be not that. This.
Iter, as long as iter is equal to loops.
Wait, no, this is the while. Wait, is this the while condition, or is it? This is the terminal condition, so it'll stop when
this is the
iter
inverse of
loops.
the terminal condition. So this is as long as it keeps going.
Right. So then this needs to be as long as it is less than loops.
Yep. Okay.
Right.
So what are we doing with I then? Why are we using iter too?
So this is I is going to be the Fibonacci number. Iter is the number of loops. So I specify the number of loops up here in the argument of the function. Iter is the number of loops, right? So that's my sort of relative placeholder for the number of loops, my iterative thing. And that's why I had I plus equals I, because that's Fibonacci, right? And so I will loop and consecutively add I to it.
Whoa. If you're changing, okay, I see what you're saying.
Until I hit, so then I go here, and I don't know if I need to do this, but plus equals 1, and then return. Once this is all done, we can have printy happy land here. That's fine. And then once this is all done, my function would return I.
Hold on, that's in the loop. So, look.
Is it? Where does it? Oh, I see. Yes. Mm-hmm.
Yeah.
That.
Okay. All right. Let's try this.
I will probably break.
I think our runtime came back.
I am good at breaking things.
Okay. Did you hit execute?
No, I can.
Okay.
Ooh, all right. Like an error is better. So let's see. First, use this in the function. I.
Okay, because this is why you wanted to put your return in the for, because I is only valid inside this loop.
I see. Hold on. No. So I do. No, I don't want to turn it. No, I don't. I want to. And I know what you told me. I can define things.
It's okay. You don't have to.
I don't want to in this particular case.
Well, you
because
don't need
I
to put,
want to be able.
Then don't put
I want
anything
to be able
here.
to. No, but I want that to be I.
Why does it need to? No, that's the initializer. So if you're not initializing anything, then.
Oh, okay. So I don't. Okay.
Yeah,
yes.
you can just omit it. It's okay.
Got it. I want that because
Okay.
I want to be able to reference I outside.
I is now available outside of the scope of the loop.
Yes.
Okay. So go ahead.
Oh no. All right. More break. Okay, let's see. When return with a value and function returning void. I don't want this to be a void. I want this to be an int.
Yep.
Poop on you. All right. Expected. I'm
gonna just clear that so we can see the next error.
Oh, I need semicolons everywhere or I get sad. All right. So.
Okay.
Right? That actually, hold on. No. So Fibonacci, we call Fibonacci 3 here, which we would expect 2 is the answer. Oh, but I need the previous one. So hold on. I equal. Give me this. Hang on. I got this. So there is the I of the loop and the I of the previous. So.
By the way, I hate Fibonacci problems. I'm sorry we did this.
No. I want to. So hold on. Let me ramble to myself for a second. So the issue here is that we're adding. When we get to 2, we're adding 2 to itself instead of the previous I. So actually what I'm going to need to do is I'm going to need a way to store the previous I value in. So yes, here's what we need. So we need to start out with.
I'm going to bring this up here.
Yeah. So we need to start out with. I'm going to start in easy land. I'm not starting with 0. All right. So I plus equals previous I. And then here, previous I equals I. Poop on you. Poop on your face.
All right. Let's walk through it. So, because I want to get done with Fibonacci too. So, okay. So you're using iter 0. So first of all, this is only used in the loop as an iteration counter. So why don't we just move that here? Right?
What? Oh, okay. Yes, that makes sense.
Okay.
Actually.
So
okay, yes.
let's just keep the iteration. So this is going to count however many times we have. It's going to run our loop however many times loops is, right? So if loops is 1, then it should just do it once. Okay. So if we do loops of 1, execute. Okay. So it prints out only once. Yep. Okay, cool. So
that's fine.
So if we did 2, you were going to see 2 lines.
That's
right?
the correct answer.
Okay. So
that's 1, 2. No, because 3. So 1 loop would create 2. The second loop should create 3.
Yeah.
So I see the problem. Hold on. Give me 1 second here. So I plus equals previous I. So that instantaneously becomes 2. I need a way to store. Wait, that can't work, can it? Can that be the thing that I want?
Well, I mean, hold on. The line we really want. Let's not be fancy for a moment. If you're using I as the current Fibonacci number, right?
Yes. Yeah.
Okay. So the thing we really want is I is going to get whatever the previous number was plus whatever the number before it was.
The previous I?
Well, I mean, 2 is the example 2 here is equal to 1
Yes. I
plus
love
1.
being able to name variables. Noxious.
Okay.
Oh, yeah.
I mean, we could use one of those as the current I if you want to stay on like the current one and we don't want to use 2 memory locations. So that's okay. So it's going to be whatever I was at the start of this loop plus previous I.
Yes.
And then previous I is going to become...
That's what I thought I was doing.
Wait a minute.
That's what I just did.
Okay, so previous I plus I... See, this is... yeah.
You built yourself this terrible. You've dug yourself into a hole here. Fibonacci is
Yeah, I know.
horrible.
No, it's good. It's good. We have to reason through this. Okay, so
We got this.
yeah, we could figure
Teamwork.
this out. Okay, so I is where are we changing I? We're adding it to whatever
the
it
previous
was.
I.
So if we started I off at 1, which is kind of what you have here, I'm going to move that down here.
Right.
So I starts off at 1. Previous I starts off also at 1.
Right.
Okay, so that, yeah, I should have put my other thing up there. Okay, so
So initially it makes sense to have I equals previous I. I think our issue when we update the
yeah, it's
definition
when we're
of previous
updating.
I.
Yeah.
Yeah.
So we start these off at 1. 1 plus 1 is 2. So great. We get the right number. And now we need to move this I to be this one. Because when we're here, when we're sort of like doing 1 and 2, and I know you can see selection now.
I can. This is so nice.
Then if this was like I, then we're going to take this thing plus previous I to get this. And then we need to move previous I to 2.
Right. I thought that's what I was doing before, but I must have made some kind of
but we're overwriting it at the same time, right?
Yeah. Okay, I see what you're saying. Yep.
Okay.
So
yeah, we can't it's like right here we just overwrote it. So we can't set...
Right. So let's I'm trying to make all these things into too many fancy pants lands here.
Okay, that's
so
fine.
How about we go?
Waste some memory. All right, that's okay.
No, just for now, because this is also this. You want to talk about like ways to do things? Is I write things the worst way possible the first time to brute force it, and then we can make it elegant.
Optimizing. I'm not worried about that.
Right.
Yep.
So now we can say previous I equals I, and then I equals new I.
Okay.
That's not the greatest way to do it, but I'm
Except
like literally
iteration
trying to
is already being incremented because that happens with the loop, right?
Right.
So why are we doubling?
But that's just we're we're not doubling our iteration. We're just we are.
Yeah, 9 we add to it each time. And then in line 13, we also add 1 to it. So we're adding 2 each loop.
Oh, no, this is C land. Okay, I don't have to spell.
Right.
We're good, right?
Yep.
So that just does it. It does it.
Yep.
That's that happy little part of the loop. Okay. All right.
Okay.
That was Python me. I'm sorry.
That's okay.
Yeah.
That's okay. We gotta make CU. Okay.
We're in sweatpants mode, not fancy pants mode. Precisely.
Okay.
Actually, I'm going to be right back really fast.
Don't you want to see if this works?
Then we will. Okay, fine. Let's see if it works.
All right, now be right back.
Okay, all right, now I'll be right
back. Okay. All right, I'll catch up on chat because I'm totally out of it. Okay, so don't forget we're in sweatpants, not fancy pants. Yes, Strophium. That's, it like try to do too many things at once and it's easy to get kind of messed up. And so what you're doing is right, but there's another problem. Try passing Fibonacci, a value like 10. Yep, not worried about iterations. I'm not sure if that refers to the previous version of what we're looking at right now. So it is what you're doing. Maybe guy hasn't seen what is wrong. Oh yeah, I wasn't looking earlier, Nathaniel. Sorry about that. I was actually just looking at the resource problem when the loop ran away. I think it ran away while she was writing, not with her end program, but at that point it was already non-responsive. Like I mentioned, I really need to get job control. I'm playing architecturally. I'm sort of messing around with this. I want to not continue down the path of running everything on the server. That was just kind of like to get started quickly. But I think that the future version of this is it's going to be more peer-to-peer as opposed to like client server, which is kind of what I have right now. So I want like, you know, somebody's going to be like running the compiler and somebody could be, you know, typing and, you know, that kind of like groupware type peer-to-peer collaboration rather than the classic client server model. So try passing. Yep. You can initialize iter inside the for loop. Yes, that's true. Yeah. Okay. So I think we're caught up if I didn't miss too much. And sorry about the music. I just paused it. The whole world is in sweatpants mode. Totally. Is that thing compiling to native or in Scriptin? It's compiling to native at the moment. I was working with the Scriptin. So the problem is you have to get it to self-host in Scriptin, and LLVM is massive, Mistran. I don't know if I'm saying your name right, by the way. Yeah, that's kind of the route that I was going with Scriptin to WASM, but self-hosting Scriptin is really nasty. Our guest is the Enceladsaurus. Oh, she's back.
Hi. Yeah, I was testing. So Strophium had said try a larger value like 10. And I would just like to demonstrate that my super awesome Fibonacci function in C does actually work, I think. I don't know really my Fibonacci numbers past like 21. It looks close enough.
I'm not too worried about it, but the runtime of this is not too bad because this is basically just going to do one for loop. Which is fine. I mean, if we were doing something a little crazier with like, you know, the general recursive version of Fibonacci, then this quickly runs away. But we already had the program run away once on us. And Mistran, yeah, no, that's cool. That you're curious because this tool is, by the way, open source. So we can talk more about that in the Q&A. I'll put that down as a topic.
How cool the thing that you built is. Yes, yeah. Please. Can we make that a topic? Because this thing is amazing. And like I keep, you know, not so subtly being like, when is this, like, when can I start to use this with the people that I'm mentoring? Yep. Because this is incredible. And if I could do this with my little brother and some folks at work that I'm teaching how to write in Python, like, oh my gosh.
Yeah, I mean, funny that you mentioned that because if you look at this drop down in the top left.
Oh my God. I see C# there.
I added a few more run times. I realized some issues with Java and C# that really has to do with the way classes work. And it really, those two are very early version because they really need multi-file support, which I haven't added yet. So the ability to use more than one. I need like a little file system navigator widget for this. But anyway, we're heading there. Okay. Let's get back to functions. So enough fun with Fibonacci. Fun. That's what we're gonna call that fun. How's that sound?
So I will save this anecdote for our after hours Scotch stream. But I do want to just say, like, ask me about my office mate, Chad. So if you remember, when we get to the after hours portion, ask me about my office mate. Okay, office mate. Because I
okay.
This is there are revelations happening for me.
Okay.
As I learn.
All right.
But yes.
Let's get through.
So I think it works.
Yes, it looks good to me. I like it. Okay. You can save this, by the way, if you want to.
Yes. Give me 1 second to copy this into my note.
Blow it away. Yeah. Oh yeah, shared selection. It showed up on my screen.
Yes, I see it on stream now.
Wow.
Right, here we go. Okay. Awesome. Okay. Thank you. Because I do like to save what we write and talk about. And I have a bunch of notes kind of commented out in my note file, but I love to copy and paste what we do so that next time I can kind of remember.
Totally. I'm going to say a little bit. We're going to save. I had a whole long thing about the actual layout of the call stack. I think we can table that. I think we did kind of enough on the call stack, but the important thing with the I'll add one more. We'll just whiteboard this instead of going into what I was going to show you before. So let me just flip back over to the whiteboard, and this thing has, okay, so we just did our first like function and it defined its own call stack. So I had main down here, and that's a great M. And you know what? Let's switch colors. What color? Pick
Green.
a color. Green. Oh, we already did.
I mean,
we already used green. You only get one use per stream. All right.
Purple.
Purple. All right.
My second favorite color. Yes.
That's probably too dark for stream.
Oh, God.
Well, no, I mean, this is all right. It's kind of magenta-ish, but so
lavender. All right, no, we're good.
Is that, let me know, chat, if that's too dark. So, so we had main and we had Fibonacci, and these. What did Fibonacci take for parameters, and what did it return?
So Fibonacci took a single int for a parameter, and it returned an int. So in that particular case, I felt like it was not one of the examples that I was concerned about.
And what did we have in Fibonacci?
In Fibonacci, we had, in addition to the specified argument loops, which was an int, and the return I, which was an int, we also had 1, 2, 3 more ints.
Okay, so they were I.
So I was, yes, that was our return. We returned I. So we already kind of specified that at the beginning.
And we had previous I.
And new I.
And new I.
But the return, when we said int Fibonacci at the beginning, that return that you said there was I. We returned I. So that's kind
that doesn't matter.
Duplicate. No.
Because the return type, the reason I say that is because the return type doesn't have a name. You'll notice in line 4 where you specified it. I'll just jump back to the learning screen.
No, int Fibonacci. Yeah, I see it.
Yeah.
So chat.
Yeah, just for chat. So
sorry, friends.
It's okay. In line 4, you'll notice this doesn't have a name, right? So the fact that you choose to return I just means that I needs to match whatever type this happens to be. So like you would get something a little bit funky if this was like, if we defined I as a char.
Yeah.
And then char I and int I don't exactly match, but it can be.
So what does that int at the beginning do? Because when we first discussed what that particular line did, oh Lord, I don't want to think about what that did. That hurts my head. What?
Yeah, we wrapped around into the sign area.
Okay, no, that actually makes sense given your explanation, so I'm fine.
And that's why we like to mind our types, because C will try to interpret it. But...
what is the point of declaring what the return type will be if it takes more memory to specify that return variable? I thought that was like setting aside. It's like staking off a little portion of memory land. This is what you get for returning. And when I return I, it's like, oh, well, I've staked this off for you, so use it. But apparently from your diagram, that is not true.
It's not exactly true. I mean, it just says that, you have I, which is a local, you're talking about an optimization, right? You're talking about if the compiler was smart enough to say this I that you declared inside the function is only going to be used as this return. So it would have to analyze the entire function to know that this I is really just going to be the return value. Right? Because the way you specify
my compiler is not smart.
Well, it depends on your compiler, to be honest. Actually, a smart compiler is going to destroy this entire routine. So let's not get into optimization
that smart
and
compiler can, let's sit down.
We're going to do the non-optimizing compiler. So we're not going to worry about that. So in the classic, literally in what you wrote, there was a return type, which was an int. So how big is an int for our purposes?
32.
Yep. 32 what's?
Bits.
Okay, which are really bytes. Now we're
4 bytes.
Okay, so we're doing 4 byte type. Okay, so we're going to allocate 4 bytes here on the stack. Okay, loops was what type?
Loops was also 4 bytes, integer.
Okay, so actually here, let me clean up this diagram. Okay, so we had some stuff. I'm not worried about main. And then we had, so in the blocks that we sort of blocked off for Fibonacci, we had return, which was 4 bytes. This is the return value. And then we had loops, which was what? It was 4 bytes, you said?
Same. Yep. Everything is pretty much int.
And then we had I in the non-optimizing case, which is 4 bytes. And because it's really just an int. And we had iter, which was also 4 bytes. Now, we could have used different sizes for these. And if we didn't worry about alignment, then we could have said, like, you know, maybe I was just a char. And that kind of got us into trouble because we actually overflowed how big I was. We could have used an unsigned char and gotten a little bit more leeway, enough for our particular example. But as soon as we started increasing the number, it would be out of control pretty quick. Okay, so this stack frame needs how much room?
Outside of main, 32.
Yeah.
Bytes.
Yeah, this stack frame is 30. This is a 32 byte stack frame. Now, the only other thing that I told you that there was a little bit more.
Right.
Okay. And the important thing that we're going to talk about in that little bit more is, what does the function need to know when it's done? What does the computer have to know when it's done running this function?
This function specifically, or
any function?
Are you abstracting? Okay.
Yeah, when a function finishes, where does it go back to?
Where does it? Do you mean
the sound of one hand clapping? That's...
So I have a couple of thoughts. So when a function finishes,
well, I mean, in this particular program that we just ran, I mean, Fibonacci was called on line 20.
It returns to main?
Yeah, I mean, it just ran, when it ran line 20, it jumped up into this new stack frame that we just drew.
Mm-hmm.
And when it finishes in that stack frame and it gets its result, where does it return to?
The previous, the stack frame that the aforementioned stack frame.
Yeah, it has to get back to basically line 21.
Line 21. Yes. Mm-hmm.
I mean, it has to,
line 19. Yeah, the scope that is line 19 to line 20.
Well, no, that's the scope, but I mean, the Fibonacci was called on what line?
20.
So next line after it?
21.
Yeah. That's, I mean, it sort of has to return, like, you know, where to go.
So, yeah, I mean, where to go is just the next line, right?
Yeah, and that's actually that little bit of memory that I just mentioned. Sometimes there's something else, which is like the registers are stored there. It depends on the particular compiler and some other stuff that we're not going to get into. But so that's the little bit of stuff that I was talking about before. But you can, the compiler can exactly this isn't guesswork. It's not like your notion of Python, right? I mean, it's not like just loosey-goosey saying, oh, you're going to get this much memory.
I'm an astronomer. I love my back of the envelope.
By the way, I love Python. I'm just telling you that, like, it's very deterministically saying, like, your memory goes from here to here, and that's it. That's your stack frame. And when you're done, you have to go back, right? You have to go back to the next line, and then we need to return the registers back to their normal state and some other stuff, you know, depending on the particular architecture.
Strophium. We're going to talk about this later, my friend. We've already had our philosophical differences aired to all of chat, so
okay.
Doesn't love Python. Wow. Okay. Sorry,
okay. Before you betrayal, get to that,
but we're fine.
Before you get to that, last topic on this. Okay.
Yes.
So that is a picture of sort of a C stack frame.
Mm-hmm. Yep.
Is that the only way we could write it?
No, because you have also said that there are frames that write bottom up, and it depends on the architecture. We have built something that looks like Intel architecture, if I remember right, yes. Which is top down.
Right. Okay. So we have a choice. We can have the stack grow down in memory. So this would be like, if we have only 256 bytes of memory, so this is a really crappy computer, then maybe this is like that calculator that I think, who was it in chat? Was it Nathaniel who was doing Mistran? So if we have 256 bytes of memory, then the stack might be at like, 255 growing down, and then however many bytes were needed is going to be your main, and then however many bytes are needed is going to be your the function you just wrote, Fibonacci, and then however many bytes are needed for any other functions that you might call. And that's fine until you hit 0, right?
Right.
All right, we just used all of the computer memory for stack, which leaves us no space for actually running the program.
Exactly.
And it leaves us no space for libraries, and it leaves us no space for heap and all sorts of other stuff. So this stack has to be sort of a fixed size. And when you grow past the size of your stack, crash.
Right. And you mentioned that earlier when that like the bottom and the top meet, it's
Yep.
uh-oh time.
Yeah.
Yep.
We can talk about the heap memory growing up. We can talk about libraries that might be M-mapped and some other stuff that's kind of in the middle. There's a lot of choices we have. We can also say in our parameters, so like, for example, add two numbers, and we gave it an X and a Y.
Mm-hmm.
How do we put those in memory?
What do you mean?
We can go left to right, so we could start with X, right? So if I'm looking at my stack frame, I could say like X goes here, and then Y goes next. Okay?
Right.
Or I could say that's going left to right, or I could say let's go right to left, and we're going to put Y first, and then we're going to put X under it.
Okay. This seems like convention. This seems just like
that's exactly what it is. So I can
Okay,
put the
good.
return
Right.
value up here. I can put the return value down here. All of these things get into the convention that I'm going to use for my calling. And that's really important because when you're in C, you're typically using something called the C declaration style, which is right to left, and the stack is unwound by the caller. So it's right to left, and it's caller unwound. So like the job of sort of like, what do you do when this function's over? Who cleans it up? Does the function clean itself up, its own stack, or does the thing that called it clean it up?
The
It's a convention.
latter,
again.
right?
Well,
Like I would guess, but
actually, both is the answer. It really depends on what you're using for a convention. It gets to exactly what you were just saying.
okay. So I mean, this is kind of like my linguistic intuition here about conventions of dictating language in terms of human languages seems to apply here, where this is all just convention.
Yeah. I mean,
Okay.
Pascal,
Referential convention.
which C was sort of being built around the same time, it was left to right, and the callee cleaned it up. Make sense?
I mean, I don't know.
I mean, so
don't
so
know
in your
Pascal, I'm
example,
sorry.
no, it's okay. I'm just saying, like, I'm just telling you, like, if you did add two in Pascal, it would be like, and it was X and Y, then on the stack it would show up like, X first and then Y second. If the stack is growing, if we're on an architecture where the stack is growing down. In C declaration, it was right to left, and the caller was responsible for unwinding the stack. The reason they did that is the problem is functions like printf. So how many arguments does printf take?
Printf takes 2 arguments.
No, it takes as many as you specify. Because you can do, we actually just did this earlier, which is why I didn't want you to delete it.
Well, one is mandatory, 2 plus are optional.
True. But how many is
Aha,
that?
yes. 2 plus to infinity.
We don't know, right?
Yeah, like I mean, it's like 2 dot dot dot
Yeah, I mean, in
is
this case,
optional.
we're calling it with three parameters. We have the specifier, we have the x and the y that match up with the specifier. If we just did printf and hello, we only have one, right?
Right.
So this is called a variadic function because it has a multiple, like it could be like, 1, it could be 2, it could be 50, whatever, right? So however the stack ends up getting built, the callee never really knows in this case. And by the way, you can't write a function like this in Pascal. It's illegal. Because the printf itself doesn't know how many arguments you're going to pass to it, right?
Yes. I mean, it knows in theory in terms of how it is defined in its own documentation. Like wherever printf is defined, it knows that it can expect mandatory 1, optional 2 to infinity argument.
No, but I'm not talking about in its specification. I'm talking about on the computer. How do we unwind the stack frame? I mean, however many you call, it's sort of up to you when you're making that call of printf. You might pass it 3, you might pass it 2, you might pass it 17.
Mm-hmm.
It's up to you.
Right.
So
yeah,
printf itself has no idea how to unwind the stack.
So then what does it?
The thing that calls printf. So if I have main and I'm calling printf with, these two parameters.
Right.
When I'm here, I know exactly how many parameters there are.
Yes.
Okay, but when I'm in this thing, I have no idea.
What do you mean by when you're in this thing?
Like if I'm implementing printf, like if you had to write the printf function, you're inside printf.
Just do some like len argument stuff.
Len? What do you mean len? Which part of memory are you going to len? You're not passing along a description of memory also. You're just passing along. Okay, here was the first thing, which was this string, which I'm skipping over how that's represented in memory. And then here was the second thing. Actually, it's C, so it's backwards. It's right to left. So it would be here's the here's the thing, and here's the %d thing as the stack is growing down. So inside of here, how do we know how many there are? At what point have we crossed into the next stack frame? Like somebody else's function? We have no idea where this line is.
Yeah. Well, I'm good. I'm glad that there's yeah, okay.
I mean, so we could change our language and say, okay, you always have to pass how many arguments there are going to be. So there are 2 arguments, right? This uses a lot of memory. And now if we're in Python, we don't really care, right? So, and that is kind of how your len works, in languages like that. Like that's pretty much how it works in JavaScript, right? There's something called arguments, and it's an array, and you could do arguments.length, and it'll tell you like, yeah, you got this many parameters. But C is just literally representing memory. So if you've done this, there's nothing here to tell you how many arguments there are.
I don't like that.
Well, I mean, that's reality.
I know. I'm just like processing it. That bothers me. But okay.
So that's actually the reason why in C, they wanted to have this support for what were called variadic functions, which could have a variable number of arguments. And so then they said, all right, well, the way we're going to solve that, we're not going to use more memory storing, the length kind of like that you specified. Instead, they're going to say, you know what, we'll just make it the caller unwinds. So it's the job of the caller, whoever calls printf, it's the job of the caller to unwind the stack and to clean up the mess.
AKA, it's your problem, not mine.
Yeah, and that is the C
Okay.
declaration.
Or user beware. Okay,
So
declarer beware.
yeah, Pascal was like, no, the callee unwinds the stack, which means you don't get to do avariatic functions. That's kind of the world that like C was being created in. So, that's like, and also things were left to right. So when we're assembling this thing and putting it onto a particular machine, we could actually look at this and say like, all right, this is how, when you call this function, pull X here, take X from here and take this %D thing from here. And in C, we had to flip the order because we're doing right to left. And there's some other speed ups. By the way, this is what Microsoft uses. So Windows uses basically a version of the Pascal calling convention, which is to say it's callee unwound, except it's right to left like C. Just because Windows.
Hashtag Windows.
Hashtag Windows. So,
Right.
so it really does matter like what kind of C compiler you're on and whatever in terms of like how it's represented in memory. The name for that is called standard call because Microsoft likes to call things standard. But even though that's actually the real standard is the C declaration syntax. So, and the funny thing is C actually allows you to specify all of these. So you can actually tack on to a function Pascal int add to, X and Y. And C is going to follow Pascal calling convention. Thank you, Nathaniel, by the way. So these are a little bit more of keywords that are available in C. They're there kind of historically. C functions had to be able to call Pascal functions. C functions work differently on Windows than they do on Linux or different Unix operating systems. And basically, the standards committee just kind of said, well, just if you don't specify, you're going to get C decl. You're going to get C style declaration. And if you do specify, then you're going to get, maybe standard call. If you're on a Windows, it'll be defaulted to that. Or, back when you were writing C code on a Mac, all of the Mac ROMs were all implemented using Pascal calling convention. So you had to literally type Pascal in front of every function whenever you were calling into the operating system. So
that sounds very much like my Max. So I'm sorry for laughing, but that's
you
like...
had to do this, like it.
Yep.
Yep. So that it's still valid syntax. You can't really take anything out of the C standard. so it's all there, but I don't think anybody would probably use Pascal calling convention. Mostly it's just down to standard call, which is kind of the Windows convention, and Linux, the world that we're running in right now, which is using the standard C declaration convention. All right. Makes sense?
70% confidence.
Areas for questions.
It's more, I would say, it's kind
or
of
just
like
needs practice.
Yeah, exactly that. So it's when I learn a new language and human language, and a new grammatical construct is introduced, and I feel, yes, I understand it, but I'm also concerned that the second that I leave this class, I won't remember it. That kind of hesitancy. So that 30% is more of like experience of learning things, telling me,
oh, sure,
you need to practice this to remember it, and less so like I'm confused.
That I totally accept that. I'm not asking if you will remember this forever. That'll just take practice. But I mean, like, overall, it's not like you're listening to any of this and you're going, no way. Why would you have different calling conventions? It's like, yeah, well, people just don't get along. I don't know. I mean, it'd be nice if all these things were standard, and they're more or less standard now. And we're going to get a little bit into the stack later. Like, we'll get into the stack when we get more into like heap space. But yeah, you could take any. Strophium says you can't take anything out of C. You could just make fun of people that use. Yeah, that's pretty much how it works in practice. Is exactly what Strophium just said. you can like that those keywords are going to be there forever. Like, and that's part of the reason the C standards committees these days, like, they're so anti adding things. Like, you wouldn't believe how many years it took to get this / syntax added for commenting.
My strength is dry graphs forever.
Okay. We're not going to get into that. I think we're safely done with our topic.
Okay.
If
I mean, I'm happy. Look at this. I wrote a function. It did something. It required a little bit of tweaking, but in the end, I remember the first Python function. I don't remember explicitly what it was, but I do remember the first time I wrote something and it did the thing I wanted it to, and it felt like victory. So,
which is awesome. There is an important thing, which is that this is part of why I was going on about stack for so long. What happens to things like previous I and iter when Fibonacci ends?
I would hope that is freed up.
Yeah, they're thrown away. That's unwinding the stack.
It's a relative reference.
I can't come down here in like line 20 and go to 21 and say, like, I can't say previous I plus 5 or something. Like, why can't I do that? Because that's a different stack frame. That's a different scope. That stuff has literally been thrown out by the caller. Make sense?
Yes. And that makes, the scope, and yes, we're good. Mm-hmm.
Okay. So I think I don't want to give you the trick question, which is,
oh no,
how do I return 2 numbers from this function?
What do you mean?
Like, right now I'm just returning the last Fibonacci number. What if I wanted the last 2 Fibonacci numbers?
I'm guessing it's not int, int I.
Nope.
So, or int, int Fibonacci.
But that's pretty good intuition, to be honest. Like, there isn't syntax for what you just described, but there is something like what you just said.
Do I just allocate double the memory?
Where? Because anywhere you allocate it inside this stack, the only thing that's going to come back is return.
Here.
Yes.
So I make that double, and then I return I, whatever.
Okay, so one option would be if we knew that, like, long.
No tuples in C. Nightshade, dude, help.
We could do something like this, and we could say, like, okay, the first, if a long is twice the size of an int, then we could take the top 32 bits and make it the first value, and the second 32 bits and make it the second value. It's kind of crazy, isn't it?
It's uncomfortable.
Yeah. That's called a bit field.
I'm sorry, I literally made a joke earlier. Long. So I now to realize that, okay. We're good. It's just I was making a joke about, in C 2000 or something, we'll have long. No, we're fine. I was sassing, but
that's totally fine. So we can use the bit field approach. Really, like, there's a couple different answers, and one of them is going to get into what we call pointers, which we're not going to cover today, but that's a future thing, and that's actually kind of where this syntax appears from, by the way, this line 19 stuff. So pointers are a way to kind of break this model and allow you to reach outside of your scope. And another way we could do it is we can build...
Oh no, pointers.
We can build pretty much what you just said, which we want to return something like a tuple, right?
Well, I was just told there are no tuples.
No, there's no tuples directly, but there's something like a tuple. It's called a struct.
Oh no! Strophium, no! Sorry, this happened yesterday where he's like, well, you've learned about structs from C, and I was like, what's a...
No, we didn't cover structs. And a struct is just a structure, which is going to be like num1, num2. And I could return a struct fib returner, and that would be basically kind of the C equivalent of your tuple. That's about as close as you could get. But we're not really going to get into structs today. Structs are all about compound types. So we're going to take our basic types and sort of put them together. That's what a struct is for. So,
well, is that a preview? It's like next time on.
That's a preview.
Strophium teaches just how to write C structs. Okay, all right. As long as this is a preview of next time and not something that you expect me to.
No, we're not.
This is disturbing.
We're
so
done.
I will.
It does lead to a problem, because the problem is this whole stack model that we just discussed, which is like there's only one spot for a return value. So that's like, how do we? Now, I mean, there's enough RAM there, but there isn't a direct way in the language to say I want a tuple. Like I want to return 2 of these things. Okay, so I think that's pretty good.